for folks who already signed in, just curiosity, how's your experience been with the TRAPS lab, and if you already started on the lazy allocation lab, how is that going? Curious to hear whether that was less painful than the page table lab. And Andrew, you want to say something about that?
I thought the TRAPS lab was okay. It was just making sure that I actually used the trampoline page properly was a little annoying.
Yeah.
But once I figured that out, then it just like kind of worked.
Good. Yeah, the whole goal of the lab was to really expose you to the trap handling, entry and exit. How about Amir? How was your experience with this with the TRAPS lab?
I thought the TRAPS lab was good, very much more manageable than the page table lab.
Good.
I noticed that there were like opportunities to be clever about some aspects of the implementation, which was nice.
Good.
And the lazy lab is good so far, debugging, but both better than the page table lab in my opinion.
Glad to hear that. I'm sure you were glad to hear that, but I'm glad to hear it too. How about Timmy? Did I?
Yeah, these two previous labs have been a lot better than the page table one. I guess the hardest part for the latest lab, the lazy one, was the read and write and all that stuff. But it's not that bad in my opinion.
Good. How about you, Catherine? How's the TRAPS lab and the lazy lab for you in comparison to the page table lab? Are you there, Catherine? I guess Catherine Wicks.
Hello, I'm doing well. Sorry, I didn't know which Catherine you're talking to. I guess there's only 20 people, so probably not likely that there's another one. I'm doing quite well.
Good. So this lab is less painful than the page table lab, or?
Yes, it is definitely less painful.
Good. Excellent.
Yeah.
Well,
the one after page tables, what was that, TRAPS? That was definitely much simpler.
Good. Okay, great. We're glad to hear that. I just wanted to get sort of an informal poll, see, the page table turned out harder than we thought it would, and so glad to hear that these ones are better. Okay, so why don't we get going? And welcome to the next lecture in 6081, wherever you are. So the topic today is about interrupts. But before jumping into sort of talking about interrupts, I wanted to share a little bit, one thing that I wanted to talk about last week, which I didn't get around doing to, and which you might find interesting. Let me see if I can get my right screen here up. So here, you see my screens here on the bottom left. I'm actually logged into Athena through the dial-up machines. And there's a couple of things I wanted to sort of talk about in terms of how memory is being used by a real operating system. Since we talked a lot about that last week, and particularly in the end of the lecture, were a lot of questions about, page out, finding free memory, and all that kind of stuff. And so this is one of the Athena machines. One thing to note, if you look at the memory line, it actually tells you how much. Okay, the program I'm running is called Top. Probably many of you have used it. You see how much memory is in a machine, and as you can see, there's quite a bit of memory in this machine. And if you look a little bit carefully, actually most of it is used. Right, a large part of the memory is actually not being used by applications, but it's actually used by the buffer cache. And so this is quite common in an operating system. You don't really want to leave your physical memory sitting idle and do nothing. you might as well use it for something useful. And so in this case, you know, a good chunk of it is actually used for the buffer cache. There's a little bit of memory free, not much. You know, fraction of like from the total memory that actually is in the machine. And so this is a very common case. Like most operating systems sort of run with basically almost no memory free at any particular instant in time. And so what that means, for example, if an application or the kernel needs some memory, it will have to throw out something. You know, maybe it has enough for a few pages or, you know, a handful of pages, but at some point, if it needs a lot of free memory, it will ask to evict something, either from the applications or from the buffer cache. And so, you know, there's sort of and so the main point here basically is that when the kernel needs to allocate memory, it's actually generally not a cheap operation, because, you know, the memory is not, there's not a ton of memory free available. The other thing that's sort of interesting to look at is I sorted the output of top by the amount of resident memory. So if you look at every line for every process, you know, you see that this is the size of the address space. And then the next line actually tells you how much memory is actually being used, like the amount of physical memory, you know, how the fraction of the address space actually is in physical memory. And as you can see, it actually, you know, is typically way smaller than the address space. And so the tricks that we talked about last were the cool ideas that virtual memory provides are being used here, like this demand paging. The shared column is shared pages, you know, from the shared libraries. And you see in general that basically the resident memory is much smaller than the virtual address space. Maybe a couple other interesting things to sort of note, just like looking at this machine. The load is very low, you know, even though there are 120 users, 102 users logged in. And you're going to see there's a lot of processes, you know, 950 or roughly. Another thing to note is actually how long the machine has been up, like 249 days. You know, your x86 kernel is probably not up that long at all, ever. Okay, so that's, you know, any questions about this? Just sort of, you know, the main point being that like most memory is in use, and the resident memory is typically much smaller than the virtual address space. And you can, of course, run this yourself if you want to and see what actually what's up. Any questions? You see some of the 6S081 students being logged in, and if you look around, you see a whole bunch of QEMUs running. Okay, no questions. Let me go back to the topic for today, which is interrupts. And the basic, you know, the basic idea is very straightforward, or what we want to enable is that there's going to be cases where the hardware wants attention now. You know, a packet comes in from the network, and so the network the network card generates an interrupt. User types a key on the keyboard, and, you know, the keyboard generates an interrupt. And, you know, what the software has to do is the software has to, you know, save its work, whatever it was doing right now, put that on the site, you know, process the interrupt, and then resume or restore, you know, the work that it was doing. And you know, basically that saving and restoring is very similar to the you know, mechanisms that we already have seen before, namely for system calls and traps, like page faults. They all use the same mechanism. So in that sense, you know, interrupts are no different whatsoever compared to traps or, you know, system calls. But there are a couple things that make them a little bit different, and why we're actually spending a lecture on them. So the three basically things that make interrupts slightly different from system calls and exceptions. One, which for a better word, I'm going to call they're asynchronous. And with that, I mean that the system call, the interrupt that happens, you know, when the hardware actually generator interrupts and then the interrupt handler runs, that interrupt handler might actually have nothing to do with the current running process on the CPU. So unlike, for example, when you do a system call, right, when the system call happens and then you jump into the kernel, then we're running in the context of the calling process. And this is not true with interrupts. They might have been completely unrelated to actually, the process that, is running in the CPU might actually have nothing to do with the interrupt handler, may not even have caused it. So that's the difference. Second of all, there is much more concurrency than we have seen so far. In fact, so this is a starting place for talking about concurrency, and we'll talk about it in Wednesday lecture a lot more. But the basic observation is that basically the CPU and the device that generate the interrupt just operate in parallel. The UART or the network card, it's just doing its thing, basically picking packets from the network, and then at some point generating an interrupt. And while at the same time, the CPU is running. It also is doing its own thing. So we have like true parallelism, going on between the device and the CPU. And we have to manage that parallelism, as we'll see in a second. And then finally, I'm going to be focused mostly on external devices like network cards and UARTs, and those have to be programmed. And basically, every device has sort of its own programming manual, in the same way that sort of RISC-V has a manual with the instructions and which registers do what. Every device actually has a similar sort of type manual with describing what registers it has, what operations you can perform, and what the device does in response to reading and writing control registers. Unfortunately, often the manuals for the devices are less clear than the RISC-V manual, and that which makes programming even more complicated. And so what I'm going to do in this lecture is actually pretty straightforward. I just want to talk about how the prompt shows up when the shell prints the prompt, and then if you type ls, how do these characters get read and actually then being displayed in the console. And in fact, so basically the rest of this lecture is about these three characters. But with all the mechanism that's necessary to actually make that happen. Any questions so far before I start diving in more a little bit deeper? Okay. So let's. So the first question maybe to ask is, where do the interrupts come from? And since I'm going to be focusing mostly in this lecture on external interrupts, not timer interrupts or software interrupts, the external interrupts here come from devices that are sitting on the board. And here's our sci-fi board that QEMU more or less emulates, with some small modifications. And we see there's actually, if you look around on the board, there's a lot of actually different devices there that, can be connected, to this board. Here's our Ethernet connector. In fact, here's a micro USB that sits over there. There's a micro SD card. There are reset buttons, and so there are all kinds of sort of lines that must be running from those devices, into the CPU. And most of this lecture is basically sort of understanding, what happens, at the CPU when the device generates an interrupt, and how to read and write then information from the device. I believe like these the 2 pins here at this expansion connector, I think one of them is UART. Is the UART send or transmission, and the other one is the UART, 0 receive line. And I think it's actually connected to both sides, the micro USB as well as to this expansion cord. And I think the UART chip itself, might actually be inside of this chip over there. Okay, so basically there's a bunch of lines running, on the board, into the CPU. So we go zoom in a little bit more in detail on the CPU. Here's a schema from the Sci5 documentation for the board or the processor or the core that the RISC-V processor we're using. And we looked at this a little bit before. And we see here basically, here are the devices right on the right side. Here's our UART0. And we know that basically this UART0 is memory mapped somewhere in the physical address space. Like all the DRAM sits on this side. We know that DRAM sits above 0x000 and below 0x0 sit are the different devices. And basically with load and store instructions to those physical addresses, we can actually program the UART. And we'll look at that in much more detail in a second. All the devices basically come into the processor, and really what happens is this platform level interrupt controller, which is called the PLIC for short, is the one that sort of manages the interrupts coming in from external devices. And so if we zoom in a little bit more, here's a diagram of the PLIC in our on-chip devices. So here we see there's 53 interrupt lines coming in from different devices. Probably every device has its own interrupt line. They come into the PLIC, and then the PLIC can route interrupts. And so, for example, depending, so here are our particular cores. In the way we run it with 3 cores, and basically, the PLIC can be programmed so that the PLIC will route interrupts to either one of these cores or to the first core that can take an interrupt, and there's a bit of flexibility. And if none of the cores can take an interrupt at this point, for example, they have disabled interrupts because they're processing another interrupt, then the PLIC will just hold that interrupt until a processor is available to take the interrupt. So the PLIC has some internal state, to keep track of that. And if you saw the documentation a little bit, the way real things are happening is the PLIC indicates that there is a interrupt pending. One of the cores, basically claims it. So that will tell the PLIC not to give it to any other core. And once the core is completely done with it, it will say like, okay, I'm done with this particular interrupt, and the PLIC will inform the PLIC that it can forget about this interrupt. Any questions about this? There's sort of the internal RISC-V interrupt structure.
Yeah, so when each heart holds the PLIC, does the PLIC have some enforcement mechanism to ensure fairness?
It's all up to the kernel to program the PLIC in whatever way it wants. The PLIC doesn't really, it's just a service of delivering the interrupts and writing them, but it is the kernel who programs the PLIC and tells where interrupts should be delivered, etc. In fact, interrupts have priorities. The kernel can decide which interrupt is more important than another interrupt. There's a huge amount of flexibility. Any other questions about the hardware? Okay. Okay, so that's sort of the hardware side of it. Let's talk a little bit here at a high level about the software side. Typically, the code that manages this device is called a driver. And basically, it is just code. Typically, of course, in the kernels that we'll be looking at, it's C code. And in x86, all the drivers are inside of the kernel, and the code, basically managing, or the drivers are all inside of the kernel. And so we got, the one that we're going to be looking a little bit today, is like UART.c is the driver for the UART chip. And if you look at the structure, sort of internal structure of that code, most drivers have a structure. I'm going to draw this not as an address space, or not intending to be as an address space, but typically when people talk about drivers, there's a bottom part and a top part. And basically the bottom part is the interrupt handler. So when the interrupt handler, when an interrupt comes in, the processor, the CPU has interrupts enabled. The interrupt will fire. The processor will, as we'll see in a second, will actually call the interrupt handler for that device and basically calls into the code here. And the interrupt handler just runs in, doesn't run in any context of any specific process. It just processes the interrupt. The top part, if you will, of the driver is where user processes or the rest of the kernel calls into. For example, in the console case, or the UART, there's a read and write interface that actually the higher level code actually calls into. And so typically the case is actually there's some queue often in the driver, and the top level code calls in, sticks characters into the into this queue, and the interrupt handler either puts also, or depending on sending or receiving, but if it's receiving, maybe the interrupt handler also will stick actually characters into queues. And we'll see that these queues basically used to decouple the top and the bottom part from each other, and allowing the device to run in parallel with the rest of the code on the CPU. And the interrupt handler, typically there's some restrictions on the interrupt handler because it doesn't run in any context, any process context. For example, you can't call copy in or copy out because the current page table might actually not be reflective of the page table of the process to which character should be copied. And so it's the upper part of the driver that generally does the interaction with user level processes and maybe calls copy in and copy out. Any questions about this high level picture? We'll look at this in quite a bit more detail, but this is sort of the main organization of a typical driver. And as you realize, there are many drivers in an operating system. In fact, it's quite common that the sum of the driver code is quite bigger or larger than the core kernel itself. And mostly because for every device you need a driver, and most computers have a lot of devices. Okay, so let's talk a little bit about programming devices. So typically programming is done using memory mapped I/O. So as we've seen in the RISC-V or in the Sci-Fi board, the devices show up at particular addresses in the physical address space, and this is decided by the device or the board manufacturer. And the operating system needs to know what where those devices are located in the physical memory space, and then basically programs them just using ordinary load and store instructions to those addresses. But basically, what these load and store instructions do is they read and write control registers of the device. And so typically when you maybe store something in one of the control registers, that causes a packet to be sent. So instead of reading and writing memory, these load and store instructions typically have side effects that cause the device to do something. And you have to look basically in the documentation of the device to actually figure out what the device does. And sometimes this documentation is very clear, sometimes this documentation is less clear. Let's just give you a little bit of a sample, Greg. There's two things I wanted to show you here. On the right side of the screen, you see the memory mapped, physical memory mapped space for the Sci-Fi board, and you see what the addresses are where particular things are mapped. where they show up in the physical address space. I shouldn't use the word map, where they actually show up in the physical address space. And so, for example, we see the Clint is, is there at 0x200. Let's see, we'll pick out another one. The plic was somewhere there too. Okay, here's the plic at 0xC000. That's the platform internet controller. And we see actually UART 0 here at this particular address. But turns out that on the QEMU that we're using has the UART actually at a different location. And that's because we use vert QEMU, which doesn't actually literally emulate the sci-fi board, but something that's very close to the sci-fi board. Okay, so that's the memory map. Or the memory map, of physical addresses, to devices. And then on the left side is just a piece of documentation for the UART. This is the 1655, 16550, and that's actually the UART chip that sits on that the QEMU emulates and that we're using to actually interact with the keyboard and the console. And this is a reasonable simple chip. There's not actually much going on in this device. There's sort of complications. Here on this table here shows the registers that the chip has, the control registers. And so, for example, control register 000. And when you do the load instruction, it holds will hold the data. If you do a store instruction, that's the register that will basically the data will be copied into to be transmitted, outside on the wire. Right? The UART is basically a device that allows you to send bits over a serial line. And the sent line is one line, and the received line is another line. And basically, you take a byte, and basically they're multiplexed or serialized on this single line, sent over to the other side. There's a UART chip sitting on the other side, and basically assembles the bit back into a single byte. And a couple other things that you can control, on this device. You can actually control the baud rate of the device to some degree. And probably most important for us is the register register 1, which is here, which is the interrupt enable register. And so we can program it to actually cause the UART to generate interrupts. And if you scroll down this document, you'll see that I'll scroll down a bit. The document actually in more detail basically describes what every bit in every register means. And for example, in the interrupt enable register, the IER register, which is the acronym for it. Then basically this is the receive line status interrupt and transmit holding register interrupt. So that's what the bits mean. And it goes on, and there's a lot more documentation that tells you what more detail what the registers are, how you can use it in polling mode or interrupt mode. We'll talk about it a little bit more. How you have to program the interrupt enable registers, et cetera, et cetera. So this turns out to be a short version of the real document. The real document from the chip manufacturer is much more has much more stuff in it, much more detail. But it's sort of sufficient for us to actually be able to talk about how to program the UART. And you can see this is like one of the most simple devices, and even that document, has quite a bit to it.
Sorry, I was wondering if you write something to the transmit holding register, and then you write again, like right after that, it makes sure that like the previous number didn't just like get overridden, right?
Yes and no. It's part of you actually, and this is one of the things that we're going to pay a bit of attention to. You tell basically your load instruction, you load some value, or store instruction, you load some value in that register, and then the UART chip, goes off and it's going to send off that byte onto the line, on the serial line, correct? And when it's done, it will generate an interrupt saying to the kernel, okay, I'm done with that byte. Now you can give me the next byte. And so the kernel and the device has to sort of follow a protocol to make sure that actually everything works out. This particular UART, that we're using has I think 550A actually internally has a 50, and I think it can buffer a bunch of characters, like I think up to 16. But you still have to sort of play this game of like you can't stick more than 16 characters into it until the device actually has told you, well, I've sent one character. Does that make sense?
Okay, yeah, thank you.
So we'll talk about that a little bit more, before we look at in a little more detail. The case study, that I'm going to go through for sort of explaining how devices and interrupts work is here's $ls. What happens when how you print. And so basically what happens is that the device, as we actually sort of discussed in a second ago, basically puts the character, the dollar in this case, into the UART. In fact, in that register that we just looked at, and then the UART generates an interrupt. At least that's the way we can set things up. Generates an interrupt when the character has been sent. And then on the other side, and so basically the way things are set up in QEMU is that on the send line, on the other side of the send line, it basically sits in another UART chip, and that actually connects to the console, to the virtual, the virtual console. The other side, what happens on LS is because you need to use the input, and so the keyboard actually is connected to the receive line. The receive line, and so basically the keyboard, you hit a key on the keyboard, the virtual keyboard in this case, your chip on that side, will serialize, the character L, send it to the UART on the other side. The other side, puts the bits, together again into one byte, and then generates an interrupt. To tell the processor, hey, there's a character available from the keyboard. And then the interrupt handle reads the byte from the UART, as we'll see in a second. And so those are the sort of two things that we want to sort of understand in more detail, actually how they work. Okay, any questions about this? Okay, so the RISC-V has a bunch of support for interrupts. And there's a number of registers that we'll see in more detail as they get used, but it's useful to know which ones there are. There's the SIE supervisor interrupt enable register, and that has a bit, 1 bit for external interrupts, like from devices like the UART, from software interrupts, which I'm not really going to talk about it, but it is possible from one CPU, from one RISC-V core to send an interrupt to another RISC-V core, and timer interrupts. And I'm not really going to talk about either, the supervisor of the software interrupts nor the timer interrupts. I'm going to focus on external interrupts. Then there's another register that we've seen before. It's called the supervisor status register, and that has a bit to disable and enable interrupts. On this particular core. So every core has, these registers, And there's in addition to these 3 bits for your individual control, when you want to have external interrupts or software interrupts or timer interrupts, there's a 1 bit that basically controls if you're going to receive interrupts at all. And so you can atomically switch from not getting interrupts to having interrupts, or the other way around, but just changing that 1 bit in the S status register. And then there's a separate register called the supervisor, interrupt pending register. And basically, the processor can use that. Once an interrupt is happened, the processor can look at the SIP to see what interrupt actually has come in. And in addition, there will be, if an interrupt happens in the SCOS register that we have seen a couple times before now, there will be an indication of what interrupt actually came in, which we'll look in a second. And of course, there's the STVEC register that basically holds the program or holds the address to which the processor switch once either a trap or a system call or a page fault happens or an interrupt happens, because basically it uses for all 3 cases the same mechanism. I'm not going to talk too much about SCOS and SVEC because we've seen it in detail before, and it basically operates exactly in the same way as system calls and page faults or other exceptions. Okay, so let's see, get a little bit of a sense how this stuff is sort of initialized. So we're not talking even about how the drivers actually work, but just to see how x86 programs this. These registers, so that we're going to be in a position, to take interrupts. Let's see if there are any questions on the chat. Just making sure that. Okay, good. Because I'm a little bit behind on the chat. So let's see a little bit on how x86 programs these registers. So let's pull up some code. Actually, let me get rid of the this window. Actually, I don't really need that either. So I'm not going to use DDB to walk through things. I'm just going to look at the particular functions that are relevant. So probably the first thing is in start.c. So when the machine boots or the processor boots, the start function is called. It runs in M mode and disables paging. Right away, because sort of later on the kernel can set up the page tables. And we see here that basically delegates all interrupts and exceptions to supervisor mode. And then it programs the supervisor interrupt enable register to take software interrupts, timer interrupts, and external interrupts. And then for good measure, because timer interrupts actually happen to come into are handled in M mode, the M mode code actually programs the timer register, and so that timer interrupts are generated. But I don't want to talk about that actually, so I'm going to go to main.c. And so see how external devices are handled. And so our first external device is the console. That's like where we print to, and we can see what console init does. So here's console init. It initializes lock. We actually care not much about that at all, at least not for this lecture. And it actually basically calls the UART init, and UART init is right here. It actually sets up the UART chip or configures the UART chip so that it's ready for use. At first actually disables interrupts. This is just a sequence you have to go through when you program it. Then you can set the baud rate. Then you set it 6 or 7 bits, 7 or 8 bit bytes, well, we parity or not. You reset the internal FIFOs that the UART has, clear out anything that actually might be in there. And then we receive, we enable interrupts for transmission and interruption. Amir, I think you raised your hand.
Yeah, I'm wondering what the baud rate is exactly.
Oh, the speed at which the line runs.
I see. Thanks.
Okay, so that's UART in it. Now at this point, the UART in principle can generate interrupts, but of course we haven't actually programmed the interrupt enabling stuff on the RISC-V processor itself. We haven't programmed the PLIC yet, so nothing really happens at this point yet. And so the next thing, if we're going to look back to main.c, we'll see a little bit scroll down. We'll see actually that the PLIC is initialized. And so let's look at that. And basically, the PLIC init code, if you looked at this table that I showed you a little while ago with the physical memory or the memory layout, the PLIC is in some particular location, correct? And the location is in kernel memory layout. We see that the PLIC is 00000, correct? Literally copied from that document. And the way we write stuff to the PLIC is basically take the number or the address for the PLIC, cast this to a 32 pointer integer because the PLIC registers are 32-bit, and then basically write a 1 to it. So this causes basically a 1 to be written to the register UART0 IRQ. And basically what this does is it enables interrupt requests from the UART. So remember the PLIC, basically routes the interrupts, and so an interrupt might come in from the left side from that picture into the PLIC, and the PLIC says like, this programs the PLIC to actually accept those interrupts. And similarly, it actually programs the PLIC to actually accept interrupts from the I/O disk, which I'm not going to talk about at all. Okay, and then we go back, to main.c, and right after the PLIC init, we see this PLIC init hard, and then basically for every core specifically, every core individually, so one core, the first core actually initializes this aspect, so basically we're taking interrupts from those devices, and then every core individually has to say, I'm interested in those devices too. And so, for example, here, every core actually calls this function. So every core says, I'm interested in interrupts from the UART, and I'm interested in interrupts from the virt.io. And you can see here, basically, this UART0 IRQ basically is a unique number, for the UART, the IRQ for the UART, and I think it was released on QEMU, that's number 10. And we're basically ignore priorities, and so we just set it to 0. Okay, and so does every CPU or every core individually, has to indicate to the PLIC that it actually is interested in receiving interrupts. Now at this point, we're, the PLIC basically, so we basically have to program the device to generate interrupts. We have programmed the PLIC, to pass interrupts on, to the individual CPUs. But the CPUs itself are not accepting interrupts yet because we haven't set the bit in the S status register yet. And so let's go back to main.c. And whatever, main.c does a bunch of more initialization, but in the end it actually calls the scheduler. And so let's go look at proc.c and the scheduler. And what we see here is like when so now basically the whole machine is sort of the processors has been set up, and the scheduler schedules looks for processors to run, but before doing any of that, it actually enables interrupts. And so we look at RISC-V, and we'll see there's basically this is a C function, and that basically enables interrupts. And as you can, not surprising, basically the only thing it does, it sets the interrupt enable bit in the S status register. So at this particular point in time, right at this instance, if there were an interrupt pending at the PLIC, then this particular core would be interrupted. And we'll see that in a second later, but at this point, interrupts are enabled. And so this is the basic setup. Any questions about this?
Oh,
Okay.
sorry. What core would be interrupted when at that point?
So every core runs a scheduler loop, correct? And whatever core calls interrupt on, or all cores will call interrupt on, but let's say there's only one core gets there first, like core 1, and if core 1 sets its interrupt enable bit, at that point it could receive an interrupt. And we'll see in a second what happens exactly at an interrupt.
Makes sense. Thank you.
Okay. Okay, so what I now want to do is look at this, how to print the dollar, the prompt at the shell prompt. And so for that, we want to go back a little bit. And I would first want to look at init again. So this was the first process that actually is being, init code execs init. And so that's basically the first process running. And one of the things that init does, it makes a device that represents the console. So here the device is created using the make not operation, and that returns a file descriptor, file descriptor 0 because it's the first file descriptor open, and then it dubs it, for standard out, and then for standard error, it dubs it again. And so this basically sets up file descriptor 0, 1, and 2 to correspond to the console. And now, and so, then it forks off the shell. And so let's look at the shell for a second. So the shell opens, or starts running with the file descriptors 1, 2, and 3, 0, 1, and 2 open, pointing to the console. And then the shell prints the character $ in a space to file descriptor 2. And so, so even though the console and the UART, are sort of all, below all this, to the application programmer, like the shell, or the person who wrote the shell, it just looks like a regular file. And so in fact, the shell itself, since it writes to file descriptor 2, has no idea what actually sits on the other side, right? And we have seen in the util lab that you can do all kinds of cool stuff with it. But here's an example where, basically the device in Unix is represented as a file. It's not different than anything else. Okay, so let's see, how this actually printing them works. So there's a printf is in the x86 user application. It's a tiny little C library which includes printf, and printf, as you've seen, is sort of in the trash lab, sort of an interesting function in itself. But in the end, it basically calls the write system call. And in our case, correct, the write system call would be file descriptor 2, and C would be hold the character $, and so we pass the address of the memory location that holds the $ to the file descriptor to write, and we ask to write 1 character. So basically every character written by the shell then results in a system call. And so now we can go and see what actually happens. So we, you have seen the system call before, so sys file. It has sys write. So here's the write system call. It grabs its arguments, the file descriptor, the number of bytes to be written, and the address of the address that contains the character $, calls then file write. So let's quickly look at file write. Okay, we're getting close to actually where the thing that we want to talk about. And here in file write, it looks what the type of the file descriptor is. If it's a pipe, we'll call the pipe functions. And if it's a device, which make not does, then it will call the write function for that particular device. And so we know that that actually is going to call the write function in the console. And so let's see what happens there. So here's console write. Grabs a lock. We don't really care about that right now. It copies in the 1 character, user either copy in, and then it calls UART put C. So that basically calls into the UART. And so you can think about the console as being the driver. We're looking sort of at the top end of the driver. And now it makes a call into UART.c to actually print the character. And so here's UART.c. So this is going to be a little bit interesting. Basically, internally, the UART keeps a buffer. So let's go back up a little bit. On the top, in fact, there's a buffer for transmission, and the buffer size is 32 characters. And there's a pointer, a write pointer, and a read pointer that are being used to sort of put these characters into the circular buffer. And I'll talk a little bit about that in more detail, but so there's a pointer, for the producer, and there's a pointer for the consumer. And in this case, the shell, if you will, is the producer, and it actually checks. The first thing it does is actually check whether the circular buffer is full. So, and the way it checks if the circular buffer is full, so it starts out in the original state is both the write pointer and the read pointer is 0, correct? There's 0 index into that buffer. If they're equal, you know that the buffer is empty. But if you add 1 to the write pointer and it's the same as the receive pointer, so for example, if you fill in 0, 1, 2, 3, 4, 5, 6, 7, 8, 19, 31, and then you're about to wrap around, you add 1. If then and it's still equal to the receive index or the read index, you know that the buffer is full. And so there's no point, you can't write anything at that point because apparently the UART is still busy, working its way through trying to send off the preceding, 31 characters or 30 characters. So in this case, if the buffer is full, the shell basically would put to sleep and put on the site, and the kernel would run some other program until the shell's been woken up and it's actually ready to send, or the UART is ready to send more data. Now, of course, in this case, this is not the case, correct? Because it's the first few characters that are being printed, so there's space in the buffer, and so basically the driver, puts the character into the buffer, updates the write pointer to go to the next slot, and then calls UART start. And basically, UART start is nothing else than sort of kicking the device and saying like, hey, go do some work for me. And basically, it first checks if the device is still busy sending the current character that I wrote recently. If the device is busy, we just go back and then we'll go to sleep probably, or we'll go to sleep. And otherwise, we'll read the character out of the buffer and put it in the transmission register that we saw earlier. And so the transmission register is just like as before. Let's look at that for a second. Basically you write the register, casts, the particular register to the whatever reg type, and then writes the value into it. And THR, the transmit holding register, is register 0, as we saw before from the documentation. Okay, so basically, where was I in start? So start basically kicks the device and saying like, hey, I got a register, I got a byte for you available to send off. And that's basically all basically if you will, the shell, the system call that, the shell called will do. And, once it actually kicked the device, it just will return to user space and the shell can go on and do whatever it wants to do. And presumably the next thing the shell will do is called the read system call to actually read input from the keyboard. But so the shell will return to user space using the standard mechanism that we have seen before, like user read, and just goes off and does its thing. And in the meantime, correct, the device has now gotten a kick to actually send some bytes off. And so at some point, we're going to get an interrupt. Hopefully, because we programmed the hardware to actually generate interrupts. Let's go a little bit back and talk a little bit about actually what happens when an interrupt happens. Okay, so what does the hardware do in this particular case, the RISC-V, do when an interrupt actually happens. So we set this interrupt enable bit in the S status register, so the processor can be interrupted. You know, let's say the keyboard, you know, raises the interrupt line, you know, goes through the PLIC, you know, the PLIC, you know, routes the interrupt to a particular core, and that core, you know, has the SIE bit set. So interrupt enable bit set. The supervisor interrupt enable bit set. So if that bit is set, the following things happen. And this will look very similar to, you know, what we've seen before. But the first thing the hardware does is clear the SIE bit. And this stops, you know, any further interrupts coming in, so that we can just deal with this interrupt first. And then if we want more interrupts, you know, we have to re-enable that bit. But, you know, this just stops further interrupts. Basically interrupts interrupting the interrupt. Then it sets the SEPC to, you know, the exception program counter to the current PC. You know, for example, if we were interrupted, you know, let's say the shell returned to user space, so it's happily running in user space, and the interrupt comes in because that one character was sent, then the program counter saved is whatever program counter was in user space. It saves the current mode. So in this case, it would be, you know, our example would be, it would save that actually the process is in supervisor mode, in user mode. Then it sets the mode, you know, to supervisor. And basically sets the program counter to STVEC, whatever value is in STVEC, right? Then that's going to be either user trap or user VEC or kernel VEC. And depending whether the interrupt happened, you know, whether, you know, we're in kernel space or in user mode. But in our example, where maybe the shell returned to user space, you know, STVEC will contain the user VEC address, and basically the hardware will resume the kernel at the instruction that is located at STVEC. And then we remember from previous lecture, you know, basically STVEC, you know, goes off and calls user trap. Okay, so in the end, we'll basically end up in user trap. And that's where we sort of pick up the story, because like, I don't really want to talk too much about the saving and restoring anymore, because one, we explained it in detail in the previous lecture, and two, you already played with it also in this last traps lab, and so you know exactly what's going on. Any questions? Okay, so here we're back in user trap, you know, the function you looked in detail at in the traps lab, and you know, we've dealt with, this is a case of system calls, and what we're going to do is, like, basically the only thing we're going to do is look at this case, which is the device interrupt. Right, so so we're gonna, that's a little bit lower here in the file. So here's the device interrupt, and it looks basically at the SCOS register and sees if this is an external interrupt. And if it's an external interrupt, it calls a function, the PLIC claim, to basically claim that particular, to claim the interrupt. So let's go back to PLIC and look at PLIC claim. And basically what it boils down to is that this particular CPU will tell the PLIC, hey, I'm claiming, you know, if it's a CPU 0 or CPU 1, it will tell the PLIC that CPU 1 is claiming this particular interrupt, and wants to claim an interrupt, and the PLIC returns which interrupts it gets. The IRQ for the interrupt that actually came in. And so in this case, that will be an interrupt for the UART and an IRQ 10. So PLIC claim will basically return 10. And then here in this code, you know, we'll look, you say, hey, is this interrupt 10? If it's interrupt 10, that must be a UART interrupt. And we basically call the UART interrupt function. And the UART interrupt function runs and basically gets the character off, you know, the UART. And the way it gets the character of the UART is basically it looks in the first register, the receive register, and gets the character out of there. And that is an integer, and then it calls console interrupt to do the rest of the work. Okay. Actually, sorry, I just did the wrong thing. We were talking about transmission. So if there was a character on the read side, then we'll call the console interrupt. But there is no character, correct, on the read side because we haven't read any. The keyboard hasn't done anything yet. We're just transmitting a character. So this will actually return -1, fall through, and then basically the only thing it will do is call it will call UART start to basically send any other characters that might be in the buffer that the shell might be stuck in there. And presumably there's another character in there because after the dollar is the space, and the write system call might, to write the space might have happened concurrently while the device was sending off. And so when the interrupt, transmit interrupt complete goes off, it will find in the buffer yet another character, the space character, and we'll send that space character off. Okay, does that make sense?
I have a high-level question, actually. Yep. So I understand the UART is like useful if I'm like using a keyboard, and like characters from the keyboard go through the UART and then through the CPU and then the kernel code that we wrote. Yep. But I'm not sure I understand what the point of the UART is when the shell is printing characters. Like the keyboard isn't being interacted with. No, that's correct. But the display is, right? So there's sort of two devices here. One is the keyboard and one is the display or the console. And the way QEMU interacts with the console is by UART, just by sending a character to the console. And then the console's job is basically to draw that character on the display. Oh, I see. Okay, thanks. And that might take a time, right? That's why this thing sort of interrupt driven. Okay. So a couple things now, I want to step back a little bit and think a little bit at a higher level what's going on. So we sort of walk through the code, we get sort of a feeling for the lay of the land, and like how the the details. But it's worthwhile to step back a second and think a little bit about what this all means. And in particular, what is interesting is interrupts and concurrency. Sort of think about interrupts from the perspective of concurrency. And this is one of the things that actually makes interrupts tricky or difficult to program. So first of all, as I mentioned a little bit earlier, the device, the UART in our case, the device and the CPU run in parallel. So one example in this scenario we just talked about, the UART is sending off, the character, to the console. And while that's happening, the CPU is just, going about its business. And in this case, returning to the shell. The shell may make another system call, for example, to write that space character. It all happens in parallel. And so we need to manage that parallelism a bit. And we already saw it a little bit, but I'm going to talk a little bit more in detail. And the type of parallelism that actually shows up here is typically called producer-consumer parallelism. And in the, well, actually, let me talk about it in a second. So we're going to talk about that in a little bit more detail. The second is that the interrupt stops the current running program, or the current program that's running. So in the case of the shell, the shell might be executing instruction like 212, and boom, interrupt comes in, and immediately at that point it's just stopped. And that's for the user space code, that's not a particularly big deal. Because when we return from the interrupt, we restore all the state of the user level program, and it will resume at that address which got interrupted. And so we have seen that with traps and page vault. And so
It actually works out reasonably well. But there's a little bit of a tricky case when the kernel itself is interrupted. So you're running in kernel mode and the kernel gets interrupted. That means that, and we'll talk a little bit more in detail, that even the kernel doesn't really sort of execute it straight sequentially. If you see one kernel instruction followed by another kernel instruction, between those two instructions, an interrupt might happen, depending whether interrupts are enabled or not. And so whether, and some piece of code, it's not good to have an interrupt in between. And in that case, the kernel might actually have to disable or enable interrupts to make basically code sequences atomic. So interrupt, enable, and disable. I'll talk about it in a second in more detail. And then sort of the third sort of concurrency problem that shows up is the interrupt handler, or maybe let me say it differently, the top of the driver and the bottom of the driver may run in parallel. So for example, in our example, the shell is going to call the write system call again, to provide the white space after it printed the dollar. And while maybe go back into the top level of the driver, it might want to add this white space to that queue that the UART actually has. But at the same time, on another CPU, it might actually take the interrupt from the UART and basically also be running in parallel, and that's sort of roughly in the same code and looking at the same queue. And so it's really true that basically the interrupt handler can run in parallel with the bottom half of the device driver might run in parallel on different CPUs, on the different CPU with the top half of the driver. And so we have to manage that a bit. And the way we're going to manage that is using locks. Because there's a shared data structure here, namely the buffer, and we're going to make sure that that buffer is updated correctly, and to make sure that only one CPU at a time basically manipulates that particular buffer. We're going to use locks, and locks is going to be the topic of Wednesday's lecture. So I'm not going to talk much about it at all, but it will show up big time on Wednesday. The thing I want to focus on is actually this producer-consumer parallelism. And this is a typical thing that shows up in drivers, and it is extremely common that, to see this. So, so producer consumer. And it's pretty straightforward. So we have seen, there's basically a buffer in the driver. In our case, I think there were 32 entries in it. So 0 to 31. And there's sort of two pointers. There's a read pointer and a write pointer. So here's the write pointer, the read pointer. If they're equal, the buffer is empty. And so when the shell, we do a write, or a put C, that basically puts the character like the dollar here and bumps up the write pointer to the next entry. So that's sort of the producer part. And the producer can keep going, filling up, all these characters until, until it hits, the read, until, if the next increment would hit the read pointer, we know that this circular buffer is full. And at that point, the producer must stop. And we saw that happening in the code a second ago, where the user, basically the UART code called sleep, and we'll put the shell on the side and start running another process. So the interrupt handler, like UART init or inter, is in this case the consumer, and basically every time when it or UART start, basically when UART init interrupts, it will look at the read pointer. If the read pointer is behind the write pointer, so the write pointer is already further, let's say the space is here too now. I don't actually know how to draw a space, but here's the space. And so the write pointer might now be here. So after the dollar is being sent, the UART sees that, I'm behind the right pointer, and that means I got to send the next one. And so, you could think about this as sort of the right, pointer, the read pointer is chasing the right pointer, and that's what's going on. Now, it could be the case that at some point the UART keeps up with the right pointer, right? And then when they're equal, and then it knows that the buffer is empty and there's nothing to do. Does that make sense?
Sorry, so this data structure is the same for all cores?
Okay, so let me go back to the code, right? And then, so this is the high level picture. And let's go back to UART. So this data structure that we just talked about is this buffer. And the 2 pointers, the write and the read pointer, are these 2 indexes, these indices. Okay? And this data structure lives in memory. And there's only 1 RAM, right? And so all the cores might be interacting with this data structure in parallel. And that's why we need locks.
Okay, I see. And my other question was for sleep.
Yeah.
How does it know to make the shell sleep? Like what is written there is just the address of this?
Yeah, let me, okay, basically the sleep call puts the current process running on the sleep, in a sleep state. We'll talk about it in next week or the week after in a great amount of detail. And it passes in the thing that it's waiting for. And in this case, that is the address, basically it has a channel ID or like a way of communicating for what it's actually sleeping on. And so in this case, it's TXR is the address of UART TXR, and the start function, once there's space again in the buffer, it will wake up. Okay, we'll call the corresponding call wake up with the UART TXR to indicate that any process that's actually sleeping on this address should be woken up. And how this exactly is implemented is something that we'll see a little bit later. Does that make sense? So these 2 calls go together, sleep and wake up. It's sometimes called conditional synchronization. Any other questions? Okay. Good. Let's see. So that is basically the whole story for printing a dollar. And as you can see, it's actually quite involved. There's a lot of pieces that working together to actually get this dollar out into the console. And something similar basically happens on the read side. So at some point, the shell has printed both the dollar and the white space, and then it will call read to basically read input from the keyboard. Right? And so now we want to just see what happens when that happening. So that starts basically in the end with file again. So now there's a read system call. If it's reading from the console, it will call it will of course file read. Sorry, not right. If it's the device, which in this case is the case, it's the console, then we call the read method for that device, and that is in console.c. And so we're going to go to console read is being called. And basically, it has the same structure as this UART. There's a circular buffer on the top. Here it is. It's an input buffer with 128 characters in it. And basically, it's the same game. It's a producer-consumer parallelism. But in this case, the shell is the consumer, correct? It actually is reading, characters off the buffer. And the keyboard is the producer. It sticks the characters into the buffer. And so, let's go back to console read. If there's nothing, if the read pointer or the read index and the write index are the same, basically the buffer is empty, and it goes back to sleep again. And so, so after it's printed the dollar and the ampersand, the shell is going to go to sleep, or the kernel will put the shell to sleep until a character comes in. And so at some point, let's say a user types in L, the first character from ls on the keyboard. That will cause the L to be sent to the UART chip on the board. That will be routed through the PLIC to some core. That core will take the interrupt. That will go to def inner. The def inner will see that was a UART interrupt, and then we'll call the function that we looked at a second ago. This goes back to the bottom where I got confused myself for a second. So in this case, it will get a character from the device, from the UART device, correct? We'll get the character L, and we'll call the console interrupt function using with the character L. So we can go back to the console. And console inner, gets the character. So now we have an L. If it's a control P, that actually prints a list in the processing list. It implements control H and control U to do backspace and control whatever. But in all other cases, basically what it does, it echoes the character back to the user by printing it to the console. And then it basically sticks the character into the buffer so that and wake up the process that's waiting for that buffer. If there's a process waiting, if it has hit new line and there's a process waiting, it will wake up the waiting process, and then the waiting process will read the characters out of the buffer. Okay, so here again we see this sort of decoupling using a buffer between the consumer and the producer, so that the producer and consumer can just run in parallel, independent, each on their own speed. And if one goes very fast, either the buffer will be empty or full, and it will block or wait until the other guy catches up. Any questions about this? Okay. Again, I want to talk basically about one more thing. And that is, I'm mostly I want to talk a little bit about sort of interrupt evolution, like what has happened over the last decades. So interrupt used to be relative to a processor reasonable fast, particularly in the used to be fast. So in the times that the original Unix was developed, that was the case, and that basically meant that the hardware is very simple, because if any really sort of serious work need to be done, the hardware could just interrupt the processor, and the processor would do it on the work, and so but the hardware itself could be reasonable, straightforward. Now interrupts are slow compared to the processor. I mean, you can see that, right? Because the interrupt handler needs to save and restore registers. It needs to take the interrupt. So there's a couple of there's a small budget of instructions that are just being used to actually serve the interrupt. And so if a device generates interrupts at a high speed, then the processor is going to have a tough time keeping up. And so you look at today's devices, basically the hardware or the device, there's a lot more work. And so basically there's a bunch of the work actually on the device itself before actually generating an interrupt. And so, and just to avoid interrupting the processor too much. Now, if you really have a high performance device, like say you have a gigabit Ethernet, and that card receives a lot of small packets, then you can actually generate, or the Ethernet itself could generate about 1.5 million packets per second. For minimal like 64-byte Ethernet packets, you do the math, you can roughly add to basically you're generating 1.5 million packets per second that you could receive. And so that basically means, one interrupt, if you did it for every packet, per microsecond. fact, a little bit more, than a little bit less than, or a little bit more than. So you basically one way to think about it, if there's one interrupt per microsecond, that is basically the operating system, the kernel, basically has a budget of like 1 microsecond of instructions to actually process that packet. And in fact, if it's 1.5 million, it's actually a little bit less than a budget of a microsecond. And so you can compute out how many instructions that is, and there's not going to be that much. And so in that case, you need to have a different plan. So like, what do you do if like the packets or the interrupts are, the packets are coming in so fast that the processor really can't keep up? And the solution to that is to, for these fast devices, is to actually something that's used, it's called polling. And instead of relying interrupts, what the CPU also could do is just keep, reading that control register and to see if there's a byte there. Like in the UART register, we just keep reading that LHR register and just check if there's a byte there. And basically, what this boils down to is that the CPU spins on the device, until device has input, has data. And this wastes CPU cycles, correct? Because while we're sort of checking that register over and over and over again to see if there's actually any data, we're not using those cycles to run another application, right? And and before what we've seen is that if there's nothing there, basically the kernel puts the shell to sleep, so that another application could run. But if we do polling, then that wouldn't happen. Now for a slow device, you clearly want not spin forever until the device finally gets around to actually doing its work. We really like to basically switch out the shell and so that we can run something else. But if the device is extremely fast, then the overhead of the interrupts is just high, and we're better off actually wasting basically polling that device, because very quickly we're going to get success. And so if waste CPUs, the device is slow, but if the device is fast, it saves saving or storing, or saves the whole entry and exit costs. And so, for example, high performance network cards, will if there's a stream of packets coming in, it actually will use polling, and the most sophisticated drivers, basically they dynamically switch between polling and interrupts. Okay. Any questions? I'm close to I guess my time budget is up. Any remaining questions? Okay, good. Then I'll see you Wednesday, and basically Wednesday we're going to continue the story of concurrency, and we're going to sort of, and parallelism. We're going to see some mechanisms to actually manage the parallelism to make sure that shared data structures get updated correctly. So see you on Wednesday.
Oh, I'm sorry. I was trying to find where my question was because I lost it. My question was in the so I saw that UART init is just being called once. Is that why there's just one buffer for all the cores to share together?
Well, there's also only one UART device. So
right.
The buffer corresponds to the one UART device that actually is being shared between all the cores. Like there might be multiple processes running on different cores, all trying to print to the console.
Okay, I see. Oh yeah, that makes sense. That makes sense.
Good.
So like only one core will do stuff with UART at a time?
Yeah, well, it's slightly complicated, but let's look at so let's say there's multiple guys writing, just for as one experiment, correct? And uh, and what we see, if there's multiple, let me actually, so here's UART put C, because the first thing you see is it actually acquires a lock. So if multiple cores are trying to put a character into the buffer, one of them is going to get the lock and none of the others are going to get the lock. And so that one guy, the one CPU that actually got the lock, acquired the lock successfully, is able to go and look at the right pointer, stick a character in if possible, and otherwise go to sleep. And and then if it's done, releases the lock, and then the next core can go in and acquire the lock and do its work. And so basically, this lock will serialize the concurrent accesses to the UART.
That makes sense. Yeah, thank you.
And on Wednesday, we'll talk in detail about locks.
Thank you.
Any further questions?
I have a question.
Yep.
So as far as I understand, why we need the lock inside the interrupt is because there's only one console and there can be multiple cores, right?
You mean this lock or?
I think so, right? Because usually we don't want to lock things inside interrupts, right?
Yeah. You asked this question by email.
Yeah.
Yes. Well, the issue is that as I mentioned earlier, the bottom half, or the interrupt handler, could run in parallel with the top half, and so one core could be doing UART put C, and another core could be running UART inner. And,
Okay.
And we got to make sure that they sort of don't get tangled up together, correct? That they serialize correctly, and the lock basically ensures that they get serialized.
Okay, that makes sense. But that does mean that sometimes like all cores could potentially be waiting for one of them to be handling this, right?
Yeah.
Yeah, because the interrupt has to wait, and then nothing else can get scheduled.
Well, presumably there's some other process may be running. It's unlikely. There's no deadlock. Okay, there is a risk of deadlock, but that's not this one. That we'll talk about on Wednesday. Presumably what this means, like if there's multiple guys called UART put C, and the buffer is full, then at some point this interrupt, they actually will release the lock. So for example, let's go back to UART put C. What actually will happen, correct, is that they will call sleep, and sleep actually takes the lock as an argument, and we'll see later why. But internally, before sleep actually puts the process definitely to sleep, it will release the lock.
Oh, I see. So basically you call sleep with the lock, and then that means, okay, release the lock while you sleep just so someone else doesn't.
Yeah, exactly.
Okay, interesting.
Yeah,
and then when you return from sleep, you just reacquire it. Okay.
You get the lock back.
Right. Yeah, that makes.
Fast to sleep has a separate story that we'll talk about in a week or 2 weeks.
That makes sense. Yeah. So I guess. I guess that wasn't that clear to me. Do all CPUs get the interrupt when somebody like sends something through UART?
No, well, depends. Depends how you program the PLIC. The way x86 is programmed to PLIC is that only one CPU, well, all CPUs might get interrupted, but
okay.
One is going to claim the interrupt.
Okay.
So if you go back to the PLIC, when you get an interrupt, you call this PLIC claim, and that CPU, that particular core is going to get the IRQ, and then basically the PLIC will remember that that IRQ is now being served and won't give it to anybody else.
I see. Okay, so just one of them will get it.
Yeah.
Randomly or no?
You can program the PLIC. Say, maybe prior to one CPU.
Oh, I see.
The PLIC
I see. So inside the inside the PLIC is the code that actually decides on who to bother.
Yeah, the PLIC is circuitry. There's no code in the PLIC, I think.
Just right. Okay.
Hardware device.
Okay,
the CPU programs.
Yeah, Yeah.
The kernel program.
Okay. Yeah, I was just gonna say, where does the PLIC code run? But yeah, it's not code, it's hardware. Okay, that makes sense. All right, thanks. I'll see you on Wednesday.
Yep. Looking forward to it.
So I got a question kind of related to the thinking about multiple cores running at the same time. So I think I recall in like one of the labs with, say, the primes question, we saw that print actually like interleaves the output often. Is that because the locks are only around like the put C, but the put C calls from multiple cores could interleave, meaning that like a single print F is not guaranteed to be atomic?
You got it.
Okay, that makes sense. All right, thank you.
You're welcome.
I have a quick question.
Yep.
So I remember reading in the that the reading said something about the timer interrupts being handled in machine mode.
Yeah.
And I was wondering where that was handled when we were doing the traps lab. Like where the switch to machine mode was happening during the traps lab, and then what we were doing.
Yeah. Okay. So great question. I'm pulling up the code. So if you look at your start, correct, and this start runs in N mode at the beginning of time when the machine boots, and it programs the timer chip. And so here's timer in it, and timer in it basically programs the clint, which is the local interrupter, to generate interrupts when a clock interrupt happens. And basically, here's probably the most important function here. It sets the machine mode trap handler to this function called timer vec. So that's written in assembly. And when a timer interrupt happens, that function is being called. And so when your kernel is running user mode or in supervisor mode, and the client generates an interrupt, raises the line, and it will switch to machine mode and call this function timer vec. In the same way, basically, as almost equivalent to what we've seen for supervisor mode and user mode. Okay?
Sure.
And then if you look in kernel vec.s, we looked at kernel vec a lot, right? I mean, that's that function that saves and restores a lot. And here's timer vec. It's basically the same sort of type of idea. It saves a couple registers so that it could do its job. And the only job it does is actually these sort of 6 lines of code here, or whatever, 5, 7 lines of code. And basically what it does, it reprograms the client to generate future interrupts, and then basically raises a software interrupt to the supervisor. So that goes to supervisor mode.
Okay.
And so then at the point at MRED, so let's say the kernel was interrupted, during a timer chip, so it went to machine mode. MRED then returns from machine mode back to supervisor mode, right? And if the interrupt was enabled in supervisor mode, at that point immediately the supervisor software interrupt will be generated.
Oh, okay.
And now basically the kernel will do the same thing, right? Basically we'll go to kernel vec, save, restore all the registers, and then go to kernel trap, and the kernel trap will see, there was a timer interrupt.
I see. And so what was the point of switching to machine mode in the first place? What exactly does it do?
I don't know what the point is, but this is like how the hardware works.
Okay, gotcha.
Actually, to work a little bit toward, there's some reasons I think why the timer chip actually goes to machine mode, but from our perspective, it would be great if we could have delegated the timer interrupt straight to supervisor mode and never had to deal with timer mode. But that doesn't work for this particular chip.
Okay, that makes sense. Thank you so much.
You're welcome.
Oh, I actually have a follow-up on this part of the code. So
keep asking questions, please.
Yeah, I saw that it allocates 32 uint 64s, but it only seems to be using three of them, right? In start.c,
in Scratch, yeah, I guess it allocates more than is necessary. Scratch is 32 is a Scratch area. The reason, so for every CPU, correct, there has to be some Scratch space. I guess we have 3 or something like that CPUs, so it basically allocates a little bit too much. But there's no harm in allocating too much.
Okay, so like it only uses Scratch 0, Scratch 1, Scratch 2,
no,
4 and 5.
4, so it uses 3. Okay, so 0 to 3, that's 4. 4 and 5, correct? So 6. So that's 6 integers. And I guess we could run with 4 CPUs, but we're running with 3, but we could run with 4. So 6 times 4 is 24. I guess we're definitely allocating a bit too much memory. I don't remember. I thought about this a while back ago, and I don't remember exactly where the 32 came from. So maybe let me double check. See if I can reconstruct that. Yep. Oh, yeah, save and restores. Okay, they're all 8 bytes, correct?
Yeah.
And it. Okay, let me get back to you. I can't recall right at the top of my head, why it is the way it is.
Okay, makes sense. Thank you so much.
You're welcome. Good questions.
Thank you.